Hey everybody, and today it's it's been a while. It's been a while since I've done any math related content, but today I am back. I've been just a little busy, and today I've said that like 3 times now. Today, for real this time, we're gonna be making linear systems of equations, but hard. Mainly with linear algebra. I've been learning some linear algebra, so we're gonna be doing a basic linear system of equations, except with matrices and inverse matrices, because why not? I didn't have anything else planned. So let's do 4x plus 3y. This equals 5. 2x plus y, and this equals 7. Now, you could, multiply the bottom equation by -2, cancel out the 4's, do some elimination, but that's boring. That's too easy. You could do Gaussian elimination, but I don't know how to do that. You could use Cramer's rule, but I also don't know how to do that. So instead, we're going to make this into a matrix vector product. So we'll have the matrix 4, 3, 2, 1, where I'm just taking the coefficients of the variables here. So 4, 3, 2, and 1. So this is like a basics, or one of our basis vectors. This is another basis vector after a transformation. And then we'll have just our variables x, y. And this equals another vector, namely what we actually want for our answer, 5 and 7. So I guess in summary, we have a vector where we have a vector and we are looking for it to land on another vector after applying a matrix transformation to it. So essentially, we want whatever our vector xy is to land on the new vector 5, 7 after we apply the transformation described by our matrix. So the way we're going to do this is we're going to divide both sides by this matrix, which allows us to divide our vector by a matrix, which is the same as multiplying by 1 over a matrix, which is the same as the inverse of a matrix. So how do we get the inverse of this matrix? For starters, we take 1 over the determinant of this, so we'll take det of, we'll call this matrix A, because I don't want to write it out. So the determinant of A, so we just do 4. 1 times 4 is 4, 2 times 3 is 6. Subtract, we get 1 over -2. So we have 1 over -2 multiplied by the adjacent of this matrix. Now, I know literally nothing about the adjacent other than how to actually compute it, which is this. I believe it has something to do with the transpose of a matrix, but I tried learning that and it was absolutely awful. I wanted to gouge my eyes out because I was doing it on a 3x3 matrix and it was absolutely terrible. So we are not going to be explaining what this means. I just know you swap some things around, change the signs, and you have the adjacent of the matrix. So you swap 4 and 1, we give the opposite sign to 2 and 3, and now we multiply by -1/2. So we get -0.5, 1.5, 1, and then -2. And this is our inverse matrix. So we'll call this A inverse. Now, let me move down a little bit. How do you move down? How do I move? It's been so long since I've used whiteboard, I legitimately don't know how to move. Lasso select, cool. How do I... Oh no, what have I done? Let's not do anything. How do I move? There we go. Okay. So now we have a inverse. All that's left is to multiply it by a matrix of our choosing, and by our choosing I mean the one I described up here, 5, 7. So matrix vector multiplication, I'm not entirely sure if this is commutative, or is it commutative or associative? But regardless, I'm not sure if order matters on this. I know order matters for matrix multiplication, so just applying 2 transformations, but I don't know if order matters for this one. So But assuming that it doesn't, we're gonna keep going. -5 or 0.5, 1.5, 1, -2, and then we just multiply it by the vector 5, 7. Now this is pretty easy. I'm gonna do it the 3 blue 1 brown way because he's been carrying my linear algebra education so far. So we're just gonna have 5 times -0.5, and then 1, and then whatever the result of this is just scalar vector multiplication. That's pretty easy. I'm gonna add it to the other scaled vector, so 1.5, and then -2. So this is pretty easy. I don't like writing down here. We're gonna drag this up here. So this comes out, our scaled vector is -2.5, or sorry, yeah, -2.5. I don't know why I put the, what is that? Okay, I don't know why I put the dot there. -2.5 and just 5. This is one vector, and then we're gonna add it to the other vector. So 7 times 1.5 is 10.5, and -14. So now that we've done this, we can just add these two, add the x's, add the y's. This comes out to 8, and the bottom y comes out to -9. So this is the vector that we want, meaning that this vector 8, 9 in our normal basis, after the transformation performed by the matrix A, will land on the new vector 5, 7. And to confirm this, of course, just like with any system of equations, we just plug our numbers back in and see if they equal. So we do 8 times 4, which is 32. So 32 minus 27. Of course, that is in fact 5. And on the bottom, we have 16 minus 9, and that is 7. So yeah, just a quick, easy, or well, the point of this video is that we made linear system of equations actually a little more difficult. There's really no point to doing this. Taking the inverse of a matrix, especially if you were to have a, well, for one, taking the inverse of a matrix is super strict in terms of requirements. You need a square matrix, you need to make sure like the determinant isn't 0, and you need a few other things. And for a matrix that is not 2 by 2, taking the transpose and eventually finding its adjugate is just absolutely terrible. So like this method legitimately has no use outside of, you know, it looks kind of cool, I guess. You can flex on people, I guess, if they're struggling with linear systems of equations, if you want to be that guy. But outside of that, there's really no reason to do this. But, you know, I thought it was kind of interesting. So yeah, thank you for watching.